Hi everyone. So far we have seen that why we want to solve linear equations and what is the geometric interpretation of linear equations. So there in the geometric interpretation we have seen the row picture, we have seen the column picture. Now to be honest, we never need this geometric interpretation, but this is just for the sake of completion. Okay. The most important part of this whole system of linear equation is this and this, which means understanding Ax equal to b intuitively and also how to solve this Ax equal to b step by step. So these two are most important point. Now let's just start with the very first point, which is understanding Ax equal to b intuitively. Okay. So let's just start this. Now suppose I write Ax that is equal to b. Now let's just start with a very basic, which means what is this a, what is this x, and what is this b. Maybe I can just rewrite it for the sake of writing. Okay, I mean my that fonts were not clear, then let me just rewrite it. So now let's just see that what is this a. As you know that a is a matrix, right? A is a matrix. And what is this x? X is a vector. And what is this b? B is also vector, right? So here what we are doing, we are multiplying a matrix which is A with a vector which is x, and then finally we are getting another vector which is b. That's what this Ax equal to b is. Now this A is a matrix and this x is a vector. Now when you multiply a matrix with a vector, then we have already seen a very nice interpretation. Let me just recall you that interpretation so that you are much familiar with Ax equal to b again. Okay. So let me just recall you that interpretation. Now suppose you want to multiply a matrix with a vector, and here in the matrix, let's suppose there are some columns. A1 is first column. So see, this A1 is not a scalar, it is a vector. Okay, I'm writing in this way, but it is a vector. This is A2, and let's suppose this is A3, and let's suppose this is x1, x2, x3. Then how you multiply? You will say that first column into this x1, which means this A1, whatever is this A1, into this x1, plus whatever is this A2 into this x2, plus whatever is this A3 into this x3. So that is how you will be multiplying this Ax, and finally you get some b. Now what do you understand from this? Can I say that Ax is nothing but this Ax? Let's not worry about this b. Okay, let's just forget this b for a moment. Let's just not worry about this b. Now let's just focus only on Ax. Can you say Ax is nothing but a vector? Because ultimately you are getting a vector from this Ax. So this Ax is a vector which is equal to b, and b is a vector, that I completely agree. But let's only focus on Ax now. Ax is a vector. What kind of vector it is? It is a vector which is obtained using the linear combination of these columns, isn't it? So you can say Ax is linear combination of columns of A. Right? So basically this Ax is a linear combination of columns of A. That's what you know. Now let's just do one thing. Let's just see some of the questions, and then we will try to make it more familiar with us, which means we will understand this Ax equal to b with more questions and with more intuition. So let's directly jump to the question so that it is permanently, permanently fit into your mind that what is this Ax. So let's just see one brainstorming question, which is, if Ax equal to 0 has some solution. They are saying that you have Ax equal to 0, and then this Ax equal to 0 has some solution. Solution always means that some value of x exists. Okay, solution means that you are solving for x. So they are saying that has some solution, which means that Ax equal to 0 can be satisfied by some x. There is some x which satisfies Ax equal to 0. See, this A here is a matrix, x here is a vector, and 0 also is a vector. Now then they're asking, then what can you say about the linear dependency of columns of A? So they're saying that Ax equal to 0 has some solution. First tell me that from this line, what do you infer? That Ax equal to 0 has some solution. What do you infer from this line? Can you say that columns of A are linearly dependent or independent or something like this? See, what is this Ax? Ax is just a linear combination of the columns, right? So this is the first column, let's suppose A1, and that is getting multiplied by x1 or maybe c1. Let's suppose x is just c1, c2, c3. This is c2, this is a2. Let's suppose this is c3, and then this is a3. So this ax, which is written here, I'm writing it in the column format, which is this, right? Now they are saying that there is some values of c1, c2, c3 that satisfy that ax equal to 0. Now what does it infer to you? Can you say that these columns are linearly dependent or independent? See, the question here is that there is some equation which is C1. Let's suppose the columns are A1, A2, A3, okay? C1, A1 plus C2, A2 plus C3, A3 equal to 0. This is the equation that is given to us, which means Ax equal to 0 is given to us, right? Now, this C here is scalar and A here is a vector and this 0 is a vector. So I'm not writing it again and again, but just for the sake of writing once, I'm just writing it, but I won't write it again and again. So basically this C here is a scalar, A1 here is a vector. Similarly, this C2 is a scalar, A2 is a vector, and then this 0 is again a vector. Okay. Now they are saying that this Ax equal to 0, which means this equation has some solution. Then what can you say about this linear dependency of A1, A2, A3? See, whenever this equation is given to you, then what is your first question? You will ask, does this exist any non-zero Ci? Okay, that still satisfy this. So you will ask, is there any non-zero Ci? If yes, if answer is yes, then they are linearly dependent. Otherwise, they are linearly independent, right? If answer is yes, then they are linearly dependent. If answer is no, then they are linearly independent. So here linearly dependent, here linearly independent. Now tell me, is there any non-zero Ci? Is this given in the question that there is a non-zero Ci or not? They are just saying that Ax equal to 0 has some solution, which means it is also possible. See that all Ci's are 0, which means that they are just saying that has some solution. So obviously there is always a trivial solution. Trivial solution means x equal to 0 will always satisfy, right? See, they are not giving any information to me. They are saying Ax equal to 0 has some solution. Obviously it has some solution. I mean, even if they do not write this line that it has some solution, I always know it has some solution. And what is that solution? X equal to 0, right? So basically when they are saying that Ax equal to 0 has some solution, they are not giving me any information. This line is completely useless. They are just saying Ax equal to 0, looking at this Ax equal to 0, okay, which has some solution. I mean, that I already know. Then what can you say about the linear dependency of columns of A? I don't know. I mean, that could be linearly dependent, could be linearly independent, right? So it depends whether I have non-zero Ci or not. See, they are not giving me any information about the Ci can be non-zero or 0. They are just saying that this has some solution, and I know that all Ci are 0, which means x equal to 0 is some solution. See, this x is nothing but C1, C2, C3 here, right? And that's how I multiplied, and that's how I got it. So if they are saying that it has some solution, then they are not giving me any information. So they are asking me that what can you say about the linear dependency of columns of A? I will say that nothing can be inferred, right? So I will say, let me just write on the next page. So from this I will say nothing can be inferred. Right? From here you can't infer anything. I hope that is understood to everyone. Now let's just see one more question. Actually this question we have already solved, but since it is in the link with the previous question, that is why let's just solve it again. So what they are saying, if Ax equal to 0 has some non-trivial solution, now they have given some information that it has some non-trivial solution. Then what does this mean? It means that this equation C1A1 plus C2A2 plus C3A3 equal to 0, this equation has some non-trivial solution. Ax equal to 0 means this equation, right? This equation has some non-trivial solution, which means there is some non-zero Ci. Non-zero Ci. It means that, let's suppose C2 is non-zero. Suppose C2 is non-zero. C2 is not equal to 0. Let C2 is not equal to 0. Okay. Then what you can do? You can basically write this A2. You can write this A2 as a linear combination of other columns. How? You will say that minus C1 upon C2 A1 minus C3 upon C2 A2 A3, right? Something like this. So basically you can divide by C2 if that is not 0, and then you can write A2 as a linear combination of other columns, which means that the columns are linearly dependent, right? So if C2 is not equal to 0, then you can write this A2, and then you can say the columns are linearly dependent. So if they are saying that there is a non-trivial solution that exists, then it means that columns are linearly dependent. Then the answer of this question is true, right? Answer of this question is true. I hope you understood why it is true. Now let's just see one more question. Suppose they say that if Ax equal to 0 has only trivial solution, which means they are giving that only trivial solution exists, there is no non-trivial solution, which means this equation that we have just talked about, this equation has only trivial solutions, right? So see, this equation which I am writing here has only trivial solution, which means that if I ask you that there is a non-zero Ci, then your answer is no, because they are saying that only trivial solution exists, which means there is no non-zero Ci, which means there is no x which is having some non-zero element, right? All has to be 0 because only trivial solution exists. Then only you can satisfy this equation. That's what is given in the question, that only trivial solution exists. So in this case you will say that since only trivial solution exists, that is why you will say that there is a non-zero Ci, the answer is no. It means that they are linearly dependent, right? If only linearly independent. If only trivial solution exists, then you will say they are linearly independent. Okay, so that's how you can solve this question. Now let's just move to more questions which are more interesting. Okay, so now in this particular video we will solve more questions which are very interesting, and then we will solve some gate PYQs. Okay, so let's just solve this question now. Okay, now let's come to these questions which are actually just dependent on our concept that we have studied in morning. So question is that suppose a matrix which is A of 3 into 3 size contains 3 linearly independent columns, which means this is a matrix A of 3 into 3 size, which means there are 3 rows, 1, 2, 3, and 3 columns, which means 1 column, 2 column, and 3rd column. Now, can anyone tell me, before reading this question, can anyone tell me this column or any column belongs to which space? Belongs to R2, R3, R5, R3. Yes, very nice. All of these columns are belonging to R3. Okay, are belonging to R3. Now I'm asking, suppose a matrix A3 by 3 contains 3 linearly independent columns. These are 3 linearly independent columns. This, and this. These are 3 linearly independent columns. Now, what can you say about number of solutions? Oh, okay, let's not worry about number of solutions. What can you say about the solutions of? Let's just talk about the solutions. Whether there is exist a solution or not. The solutions to Ax equal to B, which means they are saying you have 3 linearly independent vectors, and I give you A, I give you B, I give you B. Do you have a solution to Ax equal to B? Yuvraj is saying always exist. Yes, exist. So the solution will always be there or not? See, you have 3 linearly independent columns in R3. What does this say? Can anyone tell me? Yes, Abhipsa, that is correct. This will cover the whole space. Okay, so basically, if you have 3 linearly dependent columns in R3, then what can you say? It will fill the whole space. Which means I do not care. You give me any vector. Since I'm filling the whole space, I will give you the answer for X, Y, Z. I can generate any B. Yes, very nice. So we can generate any B. ठीक है, ये समझ में आया सबको? So see, we will be doing these kind of questions only today, and don't worry if you are not getting the first question, you will definitely get by the second or third questions. Okay, so this is okay to everyone, right? So you will say that yes, solution always exists. So what can you say about the number of solution? Let me write here. Yes, solution always exists. ठीक है? So Khushi is saying, please explain again. See, what is happening here? I am saying that there is a and there is B. Okay.
So this is given, which means that they are saying that A and B are given. Then can you get me X, Y, Z? Now the A is special here. They are saying there are three vectors which are linearly independent and all of them in R3. This is in R3. This is in R3. This is in R3. Now what does this mean to say? Suppose there are three linearly independent vectors in R3. Then can this fill the space? Filling the space means can you get any B? See, suppose there are three linearly independent vectors in R3. Maybe this 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's suppose these are three linearly independent vectors in R3. Now you give me any B, maybe 5, 6, 7. Can you get me the coefficient C1, C2, C3 or X, Y, Z or for this 5, 6, 7? Yes, we can generate any B. Very nice. So this will be basically 1, 0, 0, 0, 1, 0, 0, 0, 1. And here you can have maybe 5, 6, and 7, right? So these three linearly independent vectors can fill the whole space in R3. In fact, any three linearly independent vectors, these are just, can anyone tell me why I'm giving you this as an example? Because these are just convenient for us. That is all. Okay. There is nothing about it, but this is just convenient for us. It's not like this is very special or something. These are just convenient for humans for the calculation. That is why I am giving you this example. Otherwise, you take any three linear independent vectors in R3, you can fill the whole space. You can give me this X, Y, Z. So that's what I'm saying here. The solution means can you give me X, Y, Z? So that's what they are saying. If you have three linear independent vectors in R3, then do you always have the solution? Then answer is yes. You give me any B or you give me any A which is having three linear independent vectors in R3, I can always give you this X because these three vectors can fill the whole space. Then you give me any B. I can get you this B. Okay. Let's not worry about Abhishek is asking uniqueness, solution will be unique or not. Let's not worry about unique or number of solutions. We will just talk about the existence. Okay, uniqueness we will talk about later. Okay, let's just first understand this very clearly. Okay, so now let's see this question. Suppose a matrix which is A 3 by 4. Okay, a matrix which is having three rows. Okay, on 4 columns. So 1 column, 2nd column, 3rd column, 4th column. Can anyone tell me that these columns are in which space? Are in R, since there are 3 rows, right? So there are 3 rows. Why there are R4? Should be R3, right? So these are three. You are also making me confused. This is just R3. Like since most of the people are initially giving R4, I got confused that why it is R4. Okay, suppose a matrix A 3 by 4, which is 3 rows, 1, 2, 3, and 4 columns, then it means every vector is in R3, contains 3 linearly dependent columns. Now they are saying that among these 4, just 3 are linearly dependent. Okay, then what can you say about this Ax equal to B? For any X equal to B. Now this is having 3 linearly dependent columns. What can you say about the solution to X equal to B? Okay, solution always exists. Why? Because these 3 vectors will fill the space. What about this 4th vector? 4th vector is just redundant. Redundant means it is linearly dependent. It has to be linearly dependent. See, here I am writing B not equal to 0 because if I just write B, like B could be 0, or if I just write B could be also 0, then you will say for B equal to 0, you have the solution. I mean, the trivial solution always exists for B equal to 0. That's why, just to make the trivial things out of the picture, that's why I'm just writing B not equal to 0. Okay. Anyway, like you got it right. Why I'm writing B not equal to 0? Because if I say Ax equal to 0 has the solution or not, it does not make much sense. I mean, Ax equal to 0 always has the trivial solution. Okay. So let's not worry about this B equal to 0 or not. If you're not understanding this, then let's not worry about it. Now tell me, is this okay to everyone? If there are 3 linear independent vectors and out of these 4 vectors, then you can always get the solution. Always. Okay, always solution. Can there will be 4 linearly independent vectors? Can you have all of them as linearly independent? No. Right? In R3, you can, yes, very nice. In R3, you can only have 3 linear independent vectors. Okay. Now let's solve this question. Suppose a matrix A 5 into 4, which means 5 rows and 4 columns. one column, second column, third column, fourth column. Can you tell me what is the space of this? This belongs to R5. Yes. Contains 3 linearly dependent columns. Yeah, this is nice. They are saying out of these 4, 3 are linearly dependent, or maybe one of them, maybe fourth one is redundant. Redundant means like it depends on these columns. I mean, this is just useless. Now, what can you say about Ax equal to B, solutions to X equal to B? See, they are saying you have the R5 space, and in that you just have 3 linearly dependent columns. Then do you have the solution to X equal to B? Just think about it. Okay, yes, Vani is correct. Yuvraj is also correct. Pavan is also correct. So, see, it depends. Let's take R5. Maybe let's take 1, 2, 3, 4, 5. Okay, this is one column. Maybe another could be maybe 2. I do not know. Like, okay, I mean, I do not know whether I will be able to successfully make 3 linear dependent, but let me just try. 2, 4, 6, maybe 9, and maybe 10, something like that. And maybe 3, 6, maybe here, let me just change it to 15, something like that, and then 12, and then maybe 15, and then fourth is just a linear combination of these two. Maybe fourth, let me just take as 5, 10, 15, 20, and 25. Okay, let's take 4 columns in R5. These are the 4 columns. Out of them, let's suppose that these 3 are linearly independent. Okay, I'm not sure if these 3 are linearly independent. I'm just assuming that like I was successfully able to make it linearly independent because I was just trying to multiply by 2, and ultimately I got I just changed here 9, and maybe I also changed here 15, but I'm not sure. Actually, this is not the correct way to produce the linearly independent columns, and we do not need to do it. Let's assume that for now I'm assuming that these are 3 linearly independent columns. Okay, now let's just see if I always have the solution. Okay, let's have a B something like this. Let's have B as 1, 2, 3, 4, 5. Then tell me, do you have the solution? Yes. What is the solution? It is 1 and everything is 0. 1, 2, 3, 0. 1, 2, 3. Right? So 1 and these 3 are 0. Yes, there is a solution. If this is the case, then you can say then yes, solution. Yes, solution exists. Okay. Now let's take another example where in just R5 only, okay, maybe I have this column which is not a linear combination of these 3 columns. Maybe I will say maybe some column, I'm not sure. 3 plus 2, 5, and 6. Maybe it is 6, 12, and 21 plus 3, 24. Let me have 25 here. And then let's have some column which is actually not a linear combination of these 3 columns. Let's suppose this is not a linear combination of these 3 or these 4. This 4 is just useless. So let's say that this is not a linear combination, of these 3 columns. Okay. Suppose if it is not a linear combination, if you have some vector which is not a linear combination of these 3 columns, then can you get me this XYZ? Obviously no. Since it is not a linear combination of these vectors, these 3 vectors or 4 vectors, because 4 is just useless. You can also say 4. So you cannot give me XYZ, W or whatever, right? So it depends on A, depends on B. If this B is a linear combination of columns of A, then answer is yes. If B is not a linear combination of columns of A, then answer is no. So I will say depends on B. If B is a linear combination of columns of A, then yes. Otherwise, no. Okay. Now, if this is clear, now tell me why I was not worrying about this much in this case. Why I said like always exists. Why I have not argued that okay, if B is a linear combination of columns of A, then I have the solution. Otherwise, I do not have the solution. Why I have not said this something like this in here? Yes, very nice. It is always the case. Actually, this otherwise even does not exist. Okay, this otherwise even does not exist here, because it is filling the space. So you will always have the solution. See, here I said if it is a linear combination of columns of A, then I have the solution. Otherwise, I do not have the solution. But here this otherwise all does not exist because it is a linear combination of columns of A. You give me any B, it is a linear combination of columns of A, isn't it? So here it is not even a question whether it is a linear combination of columns of A or not. Since you are filling the space, that's why you have like you must this B must be a linear combination of columns of A. But here it depends on B. Let's suppose I have a B which is just like this copying of this. Okay, suppose I'm just copying it. Then do you have the solution? Yes, I have the solution. And how does this look like? It is 1 0 0 0. This is the solution. If I'm just copying it, maybe it depends. It depends on the B. If I'm just copying as it is one of the column, then why not? Right? If I'm having some column which is not a linear combination of these columns of A, then maybe there is no solution, right? So it depends on B basically. If B is a linear combination of columns of A, then yes. Otherwise, no. Okay. Let me know if there is any doubt. So Abhishek is asking R3, R4, etc. depends on number of rows or columns. Yes. It depends on number of rows and columns. There are 5 rows, that's why R5. Okay. Let me know if there is any doubt, or don't worry about it. You will understand this more using more examples. I understand this must be the very first time you must be dealing with these kind of things, but you will get to understand this just by using more examples. Okay. Suppose a matrix A 5 into 2 contains 3 linear independent columns, which means they are saying a matrix which is having 5 rows and 2 columns. There are just 2 columns. Okay, sorry, this should be, I'm not sure what should be the question. This should be 2 linearly dependent, I think. Let me just write 2 here. Okay, because there are only 2 columns, then how can there be 3 linearly dependent columns? Let's suppose this is 2. There are 5 rows, 1, 2, 3, 4, 5, and this is 2 linearly dependent columns. Then what can you say about solution of Ax equal to B? Let's suppose this is a vector which is obviously in R5 because there are 5 rows. This is in R5. Yes, Abhishek, that's correct. Yes, Akash. So what can you say about if this is linearly dependent? If these are linearly independent, then what can you say about the solution? Some people are saying always exists. Some people are saying may or may not be. Yes, it may or may not be, right? It depends on B. Maybe if this B is a linear combination of columns of A. See, you have always in only one case. You will say always solution in only one case. Always. You will say always solution in only one case. And what is that case? That case is that if you're filling the whole space. Okay. You will say always if you are filling the whole space. Now tell me, are you filling the whole space in this R5 just using 2 vectors? No, right? That's why you will not say always. You will not say always here. Because you are not filling the space, then how you can guarantee it? If you are not filling the space, then how you can guarantee? If you are filling the space, then you can say always. If you are not filling the space, you will say may or may not be. May or may not. Why? What does this mean, may or may not? Maybe if I have, let's suppose, these are the 2 vectors. Let me have 2 vectors maybe in R5, 1, 2, 3, 4, 5, and maybe this is 2, 4, 6, 8, and maybe 20. These are 2 linearly independent vectors, and I have this B, and this B is looking like this. Maybe let me say 1, 2, 3, 4, 5. Okay, something like that. Then do you have the solution? Yes. Because if you're just copying this, or maybe you're adding these two or whatever you're doing. Okay, if you're just copying one of them, maybe you're adding having some linear combination or something like that, then you have the solution which is 1 0. Okay, this is the solution that you have, which is 1 0, just because 1 into this and 0 into this. So basically it depends on the B. Maybe this B is not in the linear combination of columns of these 2 vectors. Maybe let me say that this B, maybe let this B be something like this. Okay, which is basically let's suppose 3, 6, 9, 12, and 20, 28. Okay, suppose okay, actually I do not know whether it is a linear combination of these two. Maybe some fraction combination can get it, but for now I'm just saying that okay, let's suppose this is not a linear combination of these 2 columns. I tried my best to make it as a not a linear combination of these 2 columns, but I cannot say. Maybe some fraction of this and some fraction of this may be making this. I'm not sure, but I tried my best by just making the difference at the last row. But maybe it is a linear combination. But for now, let's assume that this is not a linear combination. Not a linear combination of these columns. Assume. Okay, I'm just assuming it. Maybe it is a linear combination of these two columns. Suppose that this is not a linear combination of these two columns, then do you have the solution here? Can you tell me the solution? If this is not a linear combination of these two columns? No, right? There is no solution here. Yes, right. So there is no solution. Why? Because it depends on B. See, if you are filling the whole space, then you will say always. If you're not filling the space, then it depends on B. Maybe if you're just copying one of them, maybe yes. If you're not copying, or maybe if you're not having a linear combination, then answer is no. So it depends, right? I hope you got it. And you can now solve more questions. Okay, should I move to more questions? See, it is very simple. You will just say, don't worry about any doubt, it will get clear. Okay, so you will just say that that if you can fill the space, then always solution. If you cannot fill the space, then depends on B. Okay, whatever B you have depends on that. You will take a call. So basically you will say that if you can fill a space, then always solution. Okay, if you cannot fill a space, then may or may not be. Let me know if there is any doubt in these 2 points. Arpan is asking, sir, if B is not a linear combination of any vector, but we are filling the space. No, it cannot happen. Okay, if we are filling the space, then how can B not be a linear combination? If we are filling the space, it means that every vector is a linear combination. Okay, if we are filling the space, it automatically means that every vector is a linear combination of your vectors. How can we know it is filling a space or not? Okay, can anyone answer this Harsh question? Harsh is asking that how can we know we are filling the space or not? See, it depends. In Rn, if we have n linearly independent columns, then we can fill the space. Then only we can fill the space. Otherwise, we cannot fill the space. Okay, we need n linearly independent columns. See here in first example, maybe let me go to the first example. Yeah, so here I had 3 linear independent columns in R3, which means I can fill the space. Okay, I have 3 linear independent columns in R3, which means I can fill the space. I will say always solution exists because I can fill the space. You give me any B, I will give you the answer. Okay, now similarly here in this question also they are saying in R3 there are 3 linear independent columns. Yes, fourth is just redundant. Okay, this one of them is just extra, just useless. Let's not worry about this useless column. It is not useful to us, let's suppose. But we have 3 linear independent columns. Then you can fill the space or not? Yes, we can fill the space. Then always solution. Okay, here they are saying you in R5 you just have 3 linear independent. Can you fill the space? No. Do you always have the solution? No, right? So you will say that if you are having the only 3 in R5, we needed 5, but you are having only 3, then you cannot fill the space. Okay. Now similarly in R5 you are having just 2. You are having just 2. Then may or may not be solution. It depends. It depends if B is a linear combination of these 2 columns. If let's suppose if you're just copying one of them, then you have the solution. Or maybe I mean some linear combination, then you have the solution. Otherwise you do not have the solution. Okay. Let's solve more questions. You will understand things more clearly. Okay. So this question is saying, suppose a matrix A 2 into 5, which means there are 2 rows and 5 columns. Okay, 1 2 3 4 5, which means everything is in R2. Okay, contains 3 linear independent columns. Just tell about it. So they're saying so this is R2. They are saying that this contains 3 linear independent columns. Yeah, this is not possible. See, in R2, how can you have 3 linear independent columns? So first line is in fact not possible. Okay, so I just wrote it just to make you understand. Otherwise, it cannot be even a question because it is not even possible. Yeah, very nice. It is possible because in R2 we cannot have 3 linearly independent columns. Okay. Okay. So Ax equal to 0 always have one one trivial solution, which is x equal to 0. That we already know. Let's solve this question. Let's talk about this true and false. They are saying consider a matrix A with the dimension m cross n. Okay. Where m is less than n. Let me probably take this as 3, this is 4, which means this is 3 into 4. 3 rows and 4 columns, which means this is in R3. R3, okay, everything is in R3. So they are saying m into n for the system, for system Ax equal to b. What can you say about the below statement? Note that b may or may not be 0. So, okay, if it is 3 into 4, which is m less than n, then Ax equal to b always have the solution. Tell me, it always have the solution? I mean, okay, you have this just 3 into 4. And they are not saying anything about linearly dependent or independent. So maybe all of them are linearly independent. Maybe there is just one useful vector, 1, 2, 3. Everything is just dependent on them, on this. Okay. Maybe let's suppose everything else is useless. Only one vector is good. Then do you always, can you fill the space? Then answer is no. Do you always have the solution? Always have the solution? Then answer is false. Because you cannot fill the space. Right? Since you cannot fill the space, that is why answer is no. So always have the solution will be false. You understood, right? Because you cannot fill the space. Because they are saying that they're actually not giving. It is not given to us that whether this A is having linear independent columns or dependent columns. It could be anything. So if it could be anything, then do we always have the solution? No. Answer is no. If it could be anything, yeah, depends on the columns of it. Yes, very nice. ठीक है, समझ में आ गया ना? मतलब for every system we do not have the solution. System always means A and B. System means A and B. Okay, you give me any A and B of this m less than n, then do you always have the solution? And then answer is no, depends on A, right? If it is having 3 linearly dependent columns, then yes. If it is not having 3 linearly dependent columns, then no. Okay, don't worry, you will get to understand more. Let's just solve this statement. They are saying if m is less than n, maybe again let me take 2, 3, which means 2 rows and 3 columns. Okay, since there are 3 columns and there are 2 rows, this is in R2. Then there exists a system. System means A and B. So there is A and B which has a solution even if B is non-zero vector. So they are saying that you have the solution. There is a system. Okay, which means there exists a A, there exists a B. There exists A and B such that you have the solution. If these are the 3 vectors in R2, then yeah, maybe it is 1, 2. This is 1, 2. Then you have the solution which is 1, 0. Okay. Obviously, there is a system. I mean, they are not talking about anything about linear dependent, independent, but we are not even bothering about it. They are just saying, can there be values of A and B? System means values of A and B. Okay. Can there be A and B such that there is a solution? Then obviously you can just copy one of them, right? Maybe you can do this. Maybe 1, 0. Okay. Okay, let's see this. If m is greater than n, maybe this is 3, this is 2, which means there are m into n, which means there are 3 rows and 2 columns. Okay, this is in R3. Okay, ये समझ में आ गया? Why this is in R3? Because there are 3 rows. Now they are saying then none of the system means AB. Okay, AB. If none of the system has the solution, they are saying there are 2 columns, then there cannot be any system that has the solution. Tell me. Then none of the system has a solution. There cannot be A and B that has a solution. No, it's not like that. I mean, you can just copy one of them. There is A and B. There is A and B which is having the solution maybe 1, 0. So that's why it is false. So if they are saying none of the system, then answer is false. They are saying there exists a system that has the solution, then answer is true. Okay, you do not need to remember something. Okay, you do not need to remember anything. You just need to solve this analytically. Okay, you just have the situation in your hand, and then based on that you just think about it. They are saying that if you have 2 columns such that everything is in R3, this is R3, this is R3, you just have any 2 columns, and then they are saying that can there be A, can there be a B such that this is having 2 columns. Okay, then can you have the solution? Then obviously like there could be A and B such that you are just copying this one of the vector, and then you have the solution which is 1, 0. Okay. So let's solve more question, and probably after that you will get it. So they are saying for m less than n, which means, let's suppose this is 2, this is 3, which means there are 2 into 3, which means there are 2 rows and 3 columns, and everything is in R2. There is a matrix A which gives the solution of Ax equal to B for any given B. Okay, tell me. Just take your time and tell me. So if this is 2, this is 3, there is a matrix A which gives solution of Ax equal to B for any given B. Okay, these are the 3 columns. There is a matrix A. There is a matrix A. There is a matrix. Can you have a that always gives the solution? I think you can have, right? You can just have a matrix which is having 1 0 0 1, and this could be anything. This will always give the solution. Yeah, this will always give the solution because you just need a 2 linearly independent columns to always have the solution. Okay, you just need 2 linearly independent columns. Okay, everyone understood this? Now let's move to next question. They are saying for m greater than n, maybe this is 3, this is 2, which means there are 3 rows and 2 columns. This is in R3. There can be, Yuvraj is saying in the previous question, you are saying there is a for m less than n, there is a matrix A which gives the solution of X equal to B. Yeah, that is true, right? There is a matrix A which gives the solution of X equal to B for any given B. What is incorrect about it? There can be a case where sum of sum to a linearly dependent one. No, that is okay, but there exists a matrix or not? There exists a matrix, right? That can always give you the solution. Okay. Okay. Now let's go to this case. 3 is greater than 2. Then there is a matrix A which gives solution of Ax equal to B for any given B. Okay, so here they are saying you have just 2 columns in R3. Now there is a matrix A which will give you the solution for any B. Can you fill the space using these 2 columns? Then answer is no. Okay, so here the answer is false. Okay, earlier the answer was true. Okay, you got it? Because since you cannot fill the space using these 2 columns, that's why you cannot always have the solution. So there is a matrix A, then answer is no. There is no matrix A which can fill the whole space. There is no matrix which can fill the whole space. Okay, let's do this. For m equal to n, there is a matrix A which gives solution of Ax equal to B for any given B. There is a matrix A for m equal to n. So they are saying for m equal to n, maybe 3 into 3. So this is in R3, this is in R3, this is in R3. So they are saying there is a matrix which can give solution to any B. Then answer is yes, because you can fill the space. That's why answer is true. Everyone got it? Since you can fill the space using these 3 columns, that's why answer is true here.
So now let's just do one thing. Let's just solve this question as in homework. Like I will solve this in the next video, but I want you to try this question. And also I want you to try this gate PYQ. So just try these 2 questions before the next video and let me know the answers in the comment. See, this question is little tricky. Like this is true false question. You just need to tell me like which of the following is true basically. I mean the question is that which of the following is true, right? Or which of the following is false. You just need to tell me. So basically, I mean if the answer is, let's suppose you are getting T, T, F, F, T, something like this, then you can just comment out this answer. This is T, T, F, T. See, this option D is little tricky. if you can solve it now, that is okay. Otherwise, after the next video you will be able to solve this option D. But at least you can try these three options, and then you can try this gate PYQ. Okay, so let's meet in the next video. Thank you so much.